Hey guys, welcome back to another episode of the Real Hacker Hours podcast. Today I'm going to be continuing the Nightmare Reporting project, this time working on Module 8, which is dynamically linked binaries and executing effectively return to libc attacks against them. So let's begin. First, I'm going to look at Seesaw SVC first. Let's get situated here. Nightmare modules 08 off dynamic. Okay, that looks right. Let's launch Ghidra. And I should probably open up the... Let's see, what is the tip of the day? Okay, let's open up the binary in Ghidra. It's going to take me a second to get set up here. Okay, cool. So now we have everything up. Let's first take a look at the binary. Okay, cool. So 64-bit binary has NX and a stack canary, and when you run it, we get this menu looking at the write-up 64-bit binary, NX and canary found, and it gives us this menu, so it looks good. Let's see, what does the menu do? We can give it food. Okay, so looks like three options. First one takes an input, second one prints our input, third one just exits. Okay, so let's look at this write-up. So we can see that this is 64-bit, but dynamically linked binary. You can see that it's dynamically linked right there with the stack canary and a non-executable stack. When you run it, it gives us three options. We can input data, print the data, and exit. Looking through the various function user, we see that this address holds the menu we're prompted with. Is that the main function? Let's see. For 00896. That's good to go, sir. What is this address? Wait, hang on a second. 0089. Oh, I think I made a typo for 00896 from the Okay, cool. Yeah, I made a good thing I double checked. I made a typo. I forgot this 6 at the end for this function. And so, cool. Here's the function. Let's continue going through the write-up. Looking through it, we see that the menu runs in a while true loop. Okay, cool. Yeah, we see here, due to the different, when, uh, yeah, when the loop is like while just an integer, it's basically while the integer does not equal to 0. That's why this is just while bvar2, while this is while this variable does not equal 0. For each iteration, we can see that prompts us for a menu input. Okay. For the option to scan in data option, we see that it uses free to scan in. I'm just going to read silently. Say, by the way, this option gives us a buffer overflow. So we have a buffer overflow with read. Happens. Where does it happen? Okay, so that's for displaying if equals 1, so it happens right there. Cool. Scans an OX F8 bytes into this char pointer. Input. Input OXB8. Yeah, that's definitely a buffer overflow. We can see there are OXB8 bytes between the start of input and return address. A bit of Python math. We can also get this offset from the Ghidra stack layout. Okay, for this option to print it, you can see that just prints input with puts. Just gonna copy this. Just adding in the portion that we can get the stack, the offset with the Ghidra stack layout. Okay, cool. We have that for option 2. It prints with puts, which looking at here, yep, looks right. Finally, 3, you can see just if such option 3 exits the loop. So we have a buffer overflow block that we can use to return. I'm just going to read through this part. Okay, so this portion effectively just states how we're going to use. Let me think. So we have a buffer overflow for the stack, so we can overwrite the return address. However, the stack canary would prevent us. So how we're going to defeat the stack canary is we're going to leak it. How are we going to leak it? We're going to do a buffer overflow where we overwrite the null byte of the stack canary, and then use puts, which puts will just print out the entire or print a char array until it reaches a null byte. So we'll actually be able to leak the canary, and then we can just do another buffer overflow over the stack canary with itself, so we can actually overwrite the return address. And since the function that is scanning in is read, it's not something like scanf, we can input null bytes. Cool, so this portion effectively just is explaining how you overflow just the null byte of the stack canary, followed by the base pointer with the action of it. And this next portion is basically that I'm reading in the write-up. It's okay, cool. So we can overwrite the return address and actually get code execution. The question is, what code do we execute in order to get a shell? And what this portion here, I'm just going to read through it, but I'm pretty sure it's explaining just doing a puts info leak. Let me just read through it. Okay, cool. So yeah, effectively, what this last portion just explains how you do the puts and leak. Puts is an important function, meaning that it's in the PLT, meaning that there is an address in the pi segment that you can call puts. Effectively, it just calls the libc version of puts. So what we can do is we can just use that to leverage to leak an address from the GOT table, and then we have a libc leak, and then we can call code from the libc, and from there we can just from there we can effectively just call system binsh since that code is in libc. For porting it over to Python 3, this will need to be ported over, and this ROP gadget and the exploit. Let's start with this first. Wait a second. Python 3 from pwn import all elf equals elf svc print plt address plus hex elf dot puts. I'm just going to copy this next line. Okay, cool. So this has been ported over. I'm going to delete this mistake one. Okay, next up, let's do the ROP gadget. Okay, cool. That's got ported over. This is just GDB. And lastly, we just need to port over the exploit. So let's do that. Okay, let's open up the exploit. So yeah, looking at this one thing is, since we are calling code from the libc, the exploit is dependent on the libc version. Now, when I first made this write-up, I remember in here I specified, hey, it's this libc version. Actually, I'm just gonna update the libc version. So I'm just gonna update all of this. Cool. So vmap. Actually, wait. No, I'm gonna stick with the libc 2.23.ss since that's the one I used here. So I'm just gonna port the Python 2 code over to Python 3 and leave the offsets alone. Since I'm using a different libc version, the exploit, at least this one, since I'm not bothering with dealing with like the libc link, like grabbing the different linker for the libc, it's not gonna work. But I'm just gonna port the code over. Exploit. Line 27, there's a print statement I missed. Okay, yeah, these two. Line 33. Yep, this one right here. $37 right here. $76. Should probably just here. Okay, I think that's it. Okay, so the exploit can run. So the fact that it can run in Python 3 means that I port it over to Python 3 now because I don't have the libc linker set up. This exploit is not going to work. But let's go ahead and I'm just going to go ahead and test it in a separate directory because, hang on. Actually, no. I was thinking, so I made a tool a while ago. I think it's called Inspire the Liars that effectively deals with this. However, setting it up requires it takes a while since you are literally downloading a ton of different libc and different linkers. So, and I don't want to do that right now. I just want to get this done with. So I am not going to do that. I'm just going to leave this as is. But what I can do just to test it out is, so in this write-up I specified that, hey, I run it with this different libc, well, this libc version. If you're running it with a different libc version, that's cool. You just need to get these offsets and call it in this manner. What I can do is just gonna copy this binary here. And the exploit. And I can run it with GDB. And get the offsets that I need and just change it and just try running it against this one. And that should be enough of a proof of concept for me to feel comfortable with signing this off that it works. Then exploit, GOT puts. Actually, can I think one of my friends did a pull request. You could just do VM map followed by the command and it gives you the offset. Oh, it does. Oh, okay, cool. So let's do puts first since the exploit needs it. Offset is this. Wait, is that 2.31? Okay, I just wait, libc. So this is the base of libc right here. I'm concerned that it's calculating the base off of here, so I'm just going to go ahead and do this math myself. X. Something isn't right. Oh, here it is. Okay. Yeah, we see here when we do it, either I'm doing this wrong or VMAP is doing this wrong. I think VMAP is doing this wrong, but we'll see. Puts offset is this. So let's get system next. Okay, that's offset for system. Let's do binsh next. Okay, so this is the offset from the libc base to binsh. Oh, good thing I did this because we're seeing that there's a bug right here. Exploit. Okay, good thing I'm doing this. So we can see that the exploit, we're calling the system with binsh, but it's crashing in do system. This is because on like more recent versions of libc, calling it in this way, I think there's like a slight stack correctment or something like that. A slight extra thing you need to do in order to call this and actually have it not crash, which this exploit is not doing. However, when I saw this challenge initially, it was on a an older version of libc, so you could just do that just fine. I'm going to. There was one line right here. I'm just going to edit that in the exploit, so it's line 39. And just to make absolutely sure that we didn't somehow mess this up, I'm going to recopy the exploit over. Nope, that's not it. And let's edit the exploit and edit in the offsets 62580, which are right there. 30410 19258. Okay, I think the exploit ran into an issue there. Okay, yeah, the previous time it was just a minor glitch. You could see here that the exploit that we have in the write-up is actually calling system binsh, so that's solved. Okay, cool. I'm gonna go ahead and end this podcast here. Thank you, gamers, for watching. See you next time.